Hey everyone, welcome. Today, we're diving into the invisible science that's running pretty much everything around us, from the weather in the sky to the blood flowing through our veins. We're talking about fluid mechanics, the physics of, well, everything that flows. So, let's get into it.
It sounds kind of like a riddle, right? I mean, one uses this massive brute force to lift a car, while the other just elegantly glides through the air. But trust me, by the end of this, you're going to see exactly how they're both masters of the very same fundamental rules of fluids.
So here's how we're going to break it all down. First up, we'll get on the same page about what a fluid even is. Then, we're going to explore the incredible power they have when they're just sitting still. After that, we'll see what happens when we let them loose and they start moving. And finally, we'll dive into some of the weirder, hidden forces that make fluids so endlessly fascinating.
All right, first things first. Before we can get to flying planes or lifting cars, we've got to nail down the absolute basics. So, what actually is a fluid?
Now that term shear stress sounds super technical, right? But just think of it like this. It's a sideways push, kind of like when you spread butter on toast. A solid, like a brick, is going to resist that push, but a fluid? It doesn't. It just, well, it flows. And that's the key difference. It's why this one definition covers both liquids, like water, and all the gases, like the air that's all around us.
Okay, so one of the most crucial properties of any fluid is its density, which is basically just how much stuff is packed into a certain amount of space. And to make things easy on ourselves, we often use something called relative density. All that does is compare a substance to water. It's a really neat way to know if something's heavier or lighter than water without getting all bogged down in units.
All right, so we know what a fluid is, but you might be surprised to find out what it can do when it's not even moving. Yep, this is where we uncover the secrets to creating immense force and the magic of buoyancy. Have you ever felt your ears pop when you dive down to the bottom of a deep swimming pool? Yeah, that's pressure. It's literally the weight of all the water above you pushing down. And that formula you see, it might look a little scary, but all it's really saying is that the total pressure you feel, that's P, is just the regular air pressure on the surface, P naught, plus the extra pressure from the water. And that water pressure depends on the depth, H, its density, rho, and gravity, G. So the deeper you go, the bigger H gets, and pop.
So here's where it gets really cool. A guy named Blaise Pascal figured something amazing out. He realized that if you have a fluid in a sealed container, say a bottle, and you apply pressure at one spot, that pressure doesn't just stay put. Nope, it gets transmitted equally to every single part of that fluid, instantly. This is like a secret force multiplier.
And this is the magic behind the hydraulic lift. See how it works? You apply just a little bit of force on that small piston. That creates pressure in the fluid, and thanks to Pascal's law, that exact same pressure travels through the fluid and pushes up on that much larger piston. And since pressure is just force over area, that same pressure acting on a much bigger area gives you a huge output force. It's amazing. A small push on your side literally lifts a car on the other. So what about floating? And why do you feel so much lighter in a swimming pool? This goes back to Archimedes' famous Eureka moment. You know, when you get into a bathtub, the water level rises, right? That's because your body has pushed some of the water out of the way. Well, Archimedes realized that the water pushes back up on you with a force that's exactly equal to the weight of the water you just displaced. And that upward push, that's what we call the buoyant force. So, it all boils down to this, a straight-up battle of densities. If an object, like a rock, is denser than the fluid it's in, the buoyant force just isn't strong enough to hold it up and plunk, it sinks. But if the object, say a beach ball, is less dense than the water around it, the buoyant force wins the battle and it floats. It's that simple comparison that governs everything from a massive ship on the ocean to a blimp in the sky. All right, we've seen the power of fluids when they're just sitting still, but now let's crank up the energy. It's time to see what happens when fluids, well, go with the flow. Welcome to the world of fluid dynamics. This one is actually super intuitive, I promise. All you have to do is think about a regular garden hose. You've got a certain amount of water going in one end, so the same amount has to come out the other, right? Now, what happens when you put your thumb over the nozzle? You make the exit area smaller, and to get that same amount of water out, it has no choice but to speed up. That's it. That's the equation of continuity in action. Here's another great way to picture it. Think of a wide, slow-moving river. The area is really big, so the water's velocity is pretty low. But then, that same river flows into a narrow canyon. The area shrinks, and that water has to just rocket through, becoming a raging rapid.
The key thing to remember is that the total amount of fluid passing by any point every second stays exactly the same.
This is the million-dollar question, the one that connects everything. We figured out that when a pipe gets narrow, the fluid inside has to speed up. But what does that change in speed do to the pressure inside the fluid?
And the answer comes from the one and only Daniel Bernoulli. His famous theorem is basically a law about energy for fluids. Now, the full equation looks a little intimidating, I get it, but the core idea, the big takeaway, is this amazing and kind of counterintuitive relationship. Wherever a fluid is moving fast, its pressure is low, and wherever it's moving slow, its pressure is high. They're complete opposites.
And that takes us right back to our airplane wing from the beginning. A wing is shaped specifically to force the air going over its curved top to travel faster than the air moving along the flatter bottom. And according to Bernoulli, that faster-moving air on top creates a zone of lower pressure. Meanwhile, the slower air underneath keeps its higher pressure. So you have high pressure below pushing up more than the low pressure above is pushing down. And that difference, that net upward force, is what we call lift. It's that simple.
So, we've covered the big, heavy-hitting principles of pressure and flow. But fluids have a few more, let's call them hidden forces up their sleeves. And these create some of the most beautiful and strange things we see in nature.
First up, we've got surface tension. This is so cool. It's like all the molecules on the surface of a liquid are holding hands really, really tightly, creating this kind of invisible elastic skin. This is exactly why water forms little beads on a countertop, and it's how some insects can miraculously just walk on the surface of a pond without falling through.
And this constant drive to minimize its surface area explains a lot. To save energy, a liquid will always try to pull itself into the most compact shape it possibly can. And as it turns out, mathematically, for any amount of stuff, the shape with the absolute smallest surface area is a perfect sphere. And that's why nature gives us perfectly round raindrops and soap bubbles. It's just physics.
Our other hidden force is viscosity, which is really just a fancy word for a fluid's internal friction. You can think of it as how thick or sticky a fluid is. Water has really low internal friction, so it pours easily. It has low viscosity. Honey, on the other hand, has super high internal friction. It resists pouring, making it thick, slow, and, you guessed it, highly viscous.
So how can we predict if a flow is going to be smooth and orderly or totally wild and chaotic? Well, engineers have this super clever tool called the Reynolds number. It's this one value that basically combines a fluid's speed, its density, and its viscosity all into one number. If the viscosity is the dominant force, at a low Reynolds number, you get this beautiful, smooth, orderly flow they call laminar. Think of honey slowly dripping. But if the fluid's momentum wins out, at a high Reynolds number, the whole thing breaks down into chaotic, turbulent motion, like a raging waterfall.
And that brings us to our final thought. We've seen how these amazing principles, like Pascal's and Bernoulli's, let us predict and engineer incredible things. But those laws work best for smooth, predictable flow. The moment a fluid becomes turbulent, our ability to predict what it's going to do just falls apart. The beautiful, complex chaos of turbulence, the kind you see in a waterfall, in the swirling clouds, or even in distant galaxies, remains one of the great unsolved problems in all of physics. It's a powerful reminder that even in something as simple as flowing water, there are still these profound mysteries just waiting to be explored.